Welcome folks. Today I want to discuss with you in our series of geometric reasoning and geometric teaching the issue of proof. Proof in mathematics. How important the process of proof is, and to afford a child the opportunity to actually construct their own proofs in the geometry classroom. Let's have a look. The teaching and learning of proof in geometry. Well, research shows that students fail to see, let me just move my face up a bit, there we go, that students fail to see the need for proof and are unable to distinguish between different forms of mathematical reasoning, such as explanation, argument, verifying, and proof. Those four things are what builds up to being able to construct a valid and a rigorously argued proof. Explanation, creating an argument, verifying that that is indeed the case, and then proving it. Okay, now folks, there's a lot that has been published about this, so I suggest that you read more articles on proof as well. Okay, so learning to prove requires the coordination of a range of competencies, each of which is individually far from trivial. Not anybody can construct a proof. You will hear in the video series we talk about the minimum and sufficient properties. Well, prove that it is a square if those minimum and sufficient properties are in place. Is a very, very sophisticated process. There's many forms of proof that one learns about in fields like discrete mathematics. Okay, there's forms of proof that children at school find difficult, and it's our job as teachers to initiate them into this very sophisticated and expert activity that mathematicians engage with. So teaching approaches tend to concentrate on verification and devalue and omit exploration and explanation. Okay, we just said that the angle in a semicircle is a right angle. Let's quickly verify it with a proof that is just put on the board and is expected. The proof is most probably, wow, okay, yeah, it proves it to me. But the process that one has to undergo to prove that theorem is not afforded at school level. So proof is used as a verification tool. Learning to prove involves students making this difficult transmission from a computational view of mathematics to a view that conceives of mathematics as a field of intricately related features. The word related again refers to the relational. Relational. Skemp's work on relational understanding was huge and still remains huge today. So learning, I'm going to repeat that statement. Learning to prove involves students making that difficult transition from a computational view of maths, meaning maths is something that I do, okay, to a view that conceives of mathematics as a field of intricately related structures. Mathematics is the generalization of pattern. That has been argued as well. And through the habits that come later, we'll see that we will generalize through experience, through being afforded experience. And proof is one of those, folks. To turn proof into a reasoning tool is not an easy process, but it's also a thing that can be done if a teacher wants to activate that type of thinking. So learners are asked, the teaching of proof, we're still busy, the learners are asked to prove using concepts to which they have just been introduced, and to prove things that appear to be so obvious that they cannot distinguish by intuition the given from what it is to be proved. Folks, that's the perfect way to describe how we do geometry in class and why it's difficult. We give the theorem, we go and apply the theorem. We learn exponents by learning about the definition of exponents. Now we apply that definition that we just learned. Nothing else is happening. Why is it that if I multiply two like bases together, I add their powers? It's multiplication that results in addition. We need to afford the proof of that process of proof to play itself out, so that the child never forgets that 3 squared is not 6, because the process was made very clear. Well, a very, very genius man, and a man I have the world of respect for, is Professor Michael de Villiers. He's internationally known as the expert on geometry, or one of the experts, if not the expert on geometry. You can Google his name. If you Google his name, you'll go to his website, where he is really freely giving activities that teachers can use in the mathematics classroom. Very generous person. He has a wealth of knowledge. He's well respected. Let's see what he said. De Villiers points out that in addition to explanation, proof has a range of functions. It's not just to verify and explain. Those range includes communication, discovery, intellectual challenge, verification, systemization, and so forth. And I bet you as a teacher, I've never thought of that before until I've read de Villiers' work, and it changed my mind about how I use proof in the high school classroom, how I use proof in a university lecture that I might give where proof is necessary. De Villiers says these functions have to be communicated to students in an effective way if proof and proving are to be meaningful activities for them. Now, excuse me, often as a teacher of mathematics in my earlier years of teaching, I would at parents' evenings have a long queue. Your longest queues are always at the maths tables, and the parents would come, particularly once we've done geometry. But my child was so good in algebra, why can't he do geometry? And I, as a novice teacher, would say, ma'am, well, I would always fall back on this. They did not learn their proofs, which means to me they don't know their work. Did not learn their proofs. No? That was my excuse. Why? Because I told my children, well, if you battle with geometry, I've taught it to you, we've worked through problems, just go and learn your proofs. You get good marks. You get free marks by regurgitating a proof. That was not the purpose of proof. As de Villiers says here, it has to be communicated to students as an effective tool in the geometric classroom for proof to be meaningful, to be used as a tool of reasoning. Traditionally, the function of proof has been seen almost exclusively as being to verify the correctness of mathematical statements. Proof is used mainly to remove either personal doubt or the doubt of skeptics, an idea that has one-sided dominated teaching practice, one-sidedly dominated teaching practice. The idea of proof just to get your skeptical mind to show that it is indeed the case. And in most discussions and research on the teaching of proof, that is what is claimed. That is how it's used in high school classrooms, to remove personal doubt and to show and demonstrate that what we've just claimed is indeed true. Proofs as a mean of verification, of conviction, of explanation, discovery, of systemization, of communication, and of intellectual challenge. That means for proof remains at the door of the classroom and shouldn't. De Villiers argues, quite rightly so, that we should use proof as a reasoning tool, and we should provide learners with the opportunity to construct their proofs, so we can then also afford them the opportunity to learn the skills that they need when they are proving a geometric rider or solving a geometric rider. He suggests that it is likely to meaningfully to introduce the various functions of proof to students more or less in the sequence that he argues or shows below. Well, it's explanation, then discovering, it's a sequence, then providing an intellectual challenge, then verifying from that challenge the things that we have conjectured to be true. And this whole systemization of knowledge and of the process of proof, the relational features in a diagram. How do I organize those relational features to construct a proof or to solve a rider? Focusing on explanation, he argues, should counteract students becoming accustomed to seeing geometry as just an accumulation of empirically discovered facts in which explanation plays no role. Okay, so folks, it's a very short video to activate the idea of proof as a reasoning tool as we move into the Van Hille levels and the Van Hille phases of learning, as well as the geometric habits of mind. There's a task on the screen, and I'm constantly referred to this in the video series. One of the surprising results in plane geometry is that the angle in the semicircle is invariant, and that it's always equal to 90 degrees. It's Thales' theorem. Challenge to you, see how many proofs you can formulate for this theorem. Your proofs could be Euclidean, it could be focused on transformation geometry, analytical or coordinate geometry. You can use trigonometry, you can use vectors, complex numbers, you can even use matrices to prove that that is true. But try and construct as many proofs possible that you can for Thales' theorem. If this video managed to activate some thinking, please like it, share it, subscribe to my channel, and feel free to comment in the space below.